Three graphical examples of discontinuity in a function over an interval. All right, so we're talking about continuity or discontinuity. Sometimes they'll ask you to talk about continuity, sometimes they'll talk about discontinuity. So what we're looking at here are three examples, 1, 2, 3 examples of how a function can be not continuous. Right? So these are examples of how a function can be not continuous. So let's start with the first one. By the way, you do have an intuitive idea of what it means to be not continuous. Examples, let's look at the bottom over here. Right? You have 4 examples here where a function is not continuous. Let's look at the first one. Here, there's a hole right there. That's not continuous. Here, in number 2, there's a break. Right? There's a break, so that's not continuous. Number 3, there's a hole up here, and it's filled somewhere else, but that hole is big enough to make it not continuous. Or if you have asymptotes, vertical asymptotes, then we say the function is not continuous. Now, the question is, which of these do those instances describe? Okay? So if a function is not defined at a specific point, then it would say it's not continuous. So that's example 1 over here, right? At x equals c, the function does not have a value. So that's example 1, right? That fits example 1, where the f of c is undefined. All right. Let's see, number 2, where the limit does not exist. Look at example 2. Look at example 2. So if you look at the left-hand limit and the right-hand limit, they're going to 2 different places. So here the limit does not exist. All right. Now, and the last example, 3, limit as x approaches c exists, but it's not f of c. That's an example of 3. So here the limit exists, a two-sided limit as x approaches c exists, but the function value is not the same thing as the limit value, so it's not continuous. Right? So which one does number 4 represent? Which one does number 4 represent? Number 4 represents number 2. The limit does not exist. So in this example, number 4, the limit does not exist. Okay? Now, with that in mind, let's talk about what it means to be continuous. So what is the criteria of continuity? The 3 criteria of continuity. In order for a function to be continuous, all 3 of these conditions must be met. Well, so the opposite of this, f of c is undefined. F of c must exist. So f of c exists. Or we can say f of c equals some number L. Okay? All right, number 2, the opposite of this, the limit must exist. We say the limit as x approaches c of f of x exists, or let's say it's equal to some number. Right? It exists. Right? Remember, for a limit to exist, it has to be a number, or L is a number. L is some number. So L, the letter L, or the variable L, L is some number. All right? And then 3, this is it. The limit of the function as x approaches c and f of c must be the same. So we say limit x approaches c of f of x equals some limit, and that some limit is the same thing at f of c. So that's the 3 criteria. All right? That's it. Okay. That's page 53. We're going on to page 54. Now we're going to talk about what's called a removable discontinuity. So I do need to continue with page 53. What is a removable discontinuity versus a non-removable discontinuity? A removable discontinuity is like a hole here. So that's a removable discontinuity. Here at example 2, this is not a removable discontinuity because there's a massive break here. Okay? While example 3 is an example of removable discontinuity. So examples 1 and 3, 1 is a removable discontinuity because of that hole. 3 is a removable discontinuity, same reason, that hole. A non-removable discontinuity are examples 2 and 4, right? There's a big break here. No way to connect those two. And number 4, this one's going to negative infinity, positive infinity, or they could be going to both positive infinity. That if there's a vertical asymptote, it's a non-removable discontinuity. Okay? Now, there's an algebraic way where we could talk about whether there's a removable discontinuity. Okay? The algebraic one is something like this. If I have x plus 1 over x squared minus 1, if I have that situation, that's going to be a removable discontinuity. Okay? What does that mean? Well, if I rewrote this is x plus 1 over x plus 1 times x minus 1. Okay? So the x plus 1, okay, stop for a minute. Okay, so if a function has a 0 in the denominator, so in this example, if x equals negative 1 or x equals positive 1, it makes the denominator equal to 0. Therefore, it has a point of discontinuity. It's discontinuous at x equals negative 1 and x equals positive 1. When you plug in negative 1, what you have is 0 over 0. You can't have any 0 in the denominator, no matter what the numerator is. This is an indeterminate form. However, it's still also undefined. Okay, that is undefined in terms of, is it a number? It is not a number. Okay, if I plug in positive 1, it becomes 2 over 0. 2 over 0 is definitely undefined. Okay. All right. So remember, we're not taking a limit right now. All we're doing is plugging in these numbers. When we plug in negative 1, we get 0 over 0. That's undefined. When we plug in positive 1, we get 2 over 0. That's undefined. So this function is not continuous at x equals negative 1 and x equals positive 1. Now, but you can see that x plus 1s can reduce, making it 1 over x minus 1. So what I did was remove the reason for negative 1 being a point of discontinuity. So that is a removable discontinuity. So this is a very easy way to look at many removable discontinuities. This is the most common way you can get rid of removable discontinuity. There are others where the factoring doesn't work, but those are pretty uncommon. All right, let's go on to the other one. Okay, so this x minus 1 cannot be removed, right? So this x equals 1, that is a non-removable discontinuity. And the denominator factor, that will not cancel. So the x minus 1 did not cancel. It's a non-removable discontinuity. All right, let's call it there for page 53.